Coming up on this episode of the IoT Inc. Business Show.
I've sort of come around to this opinion that using data to make well-informed business decisions is certainly not a new idea, right? Successful companies have been doing this for hundreds of years. The difference is now is the ability to scale that up so quickly and so efficiently with specific kinds of software tools.
AI, and in particular deep learning, is a powerful tool for uncovering useful relationships between data, but once found, can't explain what they mean. Contrast this with humans, armed with tribal knowledge and more traditional analytics, who understand the data relationships but just can't find as many of them. In this episode of the IoT Show, I speak with Drew Conway about how to find the balance between man and machine when looking for data value.
All this and more on this episode of the IoT Inc. Business Show. The people, the business, and the technology of the next generation internet. This is the IoT Inc. Business Show. And now, here's your host, Bruce Sinclair.
Hello and welcome to the IoT Inc. Business Show. This show is made possible by sales of my book, IoT Inc., published by McGraw-Hill, and the IoT Inc. Certified IoT Professional, or ICIP, online training and certification program. Become a certified IoT professional by completing the program's 3 courses: ICIP Technology, ICIP Business, and ICIP Strategy and Digital Transformation. Details of which can be found at www.iot-inc.com. That's www.iot-inc.com. With me today on the IoT Show is Drew Conway. Drew is the CEO and founder of Alluvium, where he's responsible for the company's vision and growth. Besides running the company, he's also a data scientist, author, and speaker. Drew, welcome to the show.
Bruce, thanks for having me.
So are you a traditionally trained data scientist, or is this something that you learned on the job?
Yeah, great question, and I think one that has a lot packed into it. I would actually make the claim that even today, it would be hard to find someone who I would consider a traditionally trained data scientist.
Oh, really? Okay. Why do you say that?
Well, I think it's still a very new profession, and so the vast majority of people who are out in the professional world today with the title data scientists have probably either grown their career from something that was called a data analyst or business intelligence analyst, or made a transition from academia, which is much closer to the transition that I made, or quite frankly, are part of a more contemporary class of folks who maybe have gone through a boot camp style training camp, or even maybe a smaller group of people who I guess you could call traditionally trained, who have a master's degree in data science from one of the few universities offering it.
Yeah, so your background then, how did you get into it then?
Yeah, so for me, I was doing this style of work long before data science was a kind of known profession or known quantity. When I started my career, my title was computational social scientist, which is a big mouthful, but what it meant is I was using computational tools, so math, statistics, computer science, to answer questions around human decision making. Actually where I started my career is in the U.S. intelligence community, so I was doing this in the context primarily of supporting forward deployed special operations teams and warfighters in the Iraq and Afghanistan theater. But if we think about what the kind of core tenets of data science are even today, the largest one of them is understanding why humans make choices at large scale. And for me, I was doing that, using lots of different kinds of data, from space-based assets to ground sensing and signals intelligence, as well as very unstructured data like reconnaissance photos or reports from the ground. And the tools of the time, this is the early 2000s, were very, very early versions of what we sort of think about as the kind of commodity stack of big data tools as they exist today. And so I learned a tremendous amount about what would ultimately become the set of tools that I use in data science work, things like statistical programming, distributed computing, and, relatively, sort of straightforward machine learning and computer vision problems. But as I progressed through my career, I saw exactly the same kinds of questions, obviously not the same application of questions, being asked by media companies, social media companies, financial services companies, all of which now are very much in the data science business.
So yeah, I think that's true. Most people I ask that question have not the same answer, but a similar answer, in that they've been doing it for a while. It was maybe called something different. Now the tools are in place. Now there's a name for different job. But it's interesting because my son, who is just finishing up his freshman year, he's going to Virginia Tech, and he chose that school because it's only one of, I think, 5 schools that offer. Well, his program is called Modeling and Data Science, Computational Modeling and Data Science. So there's only one of 5 or 6 schools in the country that offered a bachelor degree. And so this is cutting edge. And the same thing, we're looking at masters, you got a few more there, but it is a very new field, but it seems to be all of a sudden the hottest thing around, right?
Absolutely. And I think, that's a double-edged sword. Obviously, the sort of the hype and excitement around data science as a profession has, increased awareness. It's certainly increased the value of folks who are doing these things, but I think it's also increased the amount of noise around what people actually do as data scientists, right. Which today, I think you still see quite a bit of variation, depending on size of the organization, particular vertical that it's in, tradition of using data and software tools to make decisions. I mean, I've sort of come around to this opinion that, using data to make well-informed business decisions is certainly not a new idea, right? Successful companies have been doing this for hundreds of years. The difference is now is the ability to scale that up so quickly and so efficiently with specific kinds of software tools. So, for me, back in, I guess it's 2010, I created something called the data science Venn diagram, which even today persists as a very well shared and often referenced kind of tool or image and reference for what data science is. And even back then, almost 10 years ago now, my idea around data science was this sort of de facto interdisciplinary discipline, that there was no single kind of either computer science or social science or statistics or math, any one discipline that would actually give you everything that you needed to do to be able to do data science. You had to have a kind of spread of the ability to use software tools, which I called hacking skills, right? The ability to actually get in and work with data at using computational systems. You had to have some background and grounding in the actual mathematics and theory of statistics, because if you didn't have that, then you wouldn't really even know how to use the tools that you were using them, or even more importantly, how to interpret the results that you were getting. And then the final piece is really, where do the questions come from, right? The area that I called the substantive expertise. And in a business context, that is, what are the business problems that you're trying to solve as a person or as a company? What are the questions that you want to interrogate with this data? Because if you don't have that, then maybe you're just you're an R&D group doing research. If you're at a university, that's fine. But if you're at a business, that's very costly. And so having a combination of these things is what I think data science as a discipline is, but it's not what I think a data scientist should do. I think, data scientists can be very deep on one or more of those dimensions, but it's very hard to find one person who does all of those things really well. And I think that either the Venn diagram itself or that general attitude of this kind of unicorn-like person who could do all these things, I think that's contributed negatively to the growth of the discipline, because it's sort of created this artificial exclusivity of the role, which I think hopefully will outgrow over the course of the next few years.
Well, that's interesting. I did not know you were the author of that Venn diagram, because I know that Venn diagram. And,
Oh yeah.
Yeah, and I remember being associated with the unicorn, as you mentioned. But I think if nothing else, you've contributed, because a lot of companies that I speak to arrange their teams around those three circles, I guess, within the Venn diagram. Like you said, the statistical knowledge, the programming knowledge, and the domain experience, or the domain knowledge. And so often this is how teams are organized. So that makes sense, right? If you can't find the one person.
Right, exactly, and it's very good to hear that. It makes me hopeful that there is a transition happening in how teams are being organized and how businesses are adopting data science. I think the work to be done certainly is where we started, which is at the training level. What kind of a data scientist do you want to be? I think there's an interesting emergent set of roles that are starting to specialize and breaking away the kind of research and development and more academic part of data science, which is great if you're a large tech company and you can invest in professors and PhD level researchers who can build you really, really innovative software, even at an experimental level. But then there's actual productionizing and deployment of code into real world environments, which often there is a big gap, right, between what works as an experiment and what works for a business to make money. And so I think the idea that having folks who come more from a purely software engineering background, who understand the limitations and the challenges of doing efficient computation at large scale to answer questions from data is, I think there's titles like data engineer or machine learning engineer that I'm seeing start to emerge that I think are great. And then, on the business side, having folks who are kind of data product managers. I've seen a couple companies.
I've not seen that. That's interesting.
Yeah. And I think it's an interesting, one of the things that is somewhat missing, I think, in data science as a technical discipline is there is no real theory of management, so to speak. In software engineering, there's lots of theories of management, about how to run an agile team and how to run scrums and doing tasking and all kinds of ways of sort of measuring progress and understanding how to assign roles and sizing work and things like that. And folks learn that stuff and they kind of grow up, and some of them become technical managers or VPs of engineering. But for senior data science folks, I think outside of the traditional kind of research or lab-based way that work gets organized, if we need to, produce a new, say, feature in a product that's based on some machine learning algorithm, there's a lot less structure that I've seen that folks have really seen work in terms of how do you go from idea to experimentation to testing to deployment, kind of full end, and then once it's deployed, how do you know it's doing well? These are kind of open questions in my mind. And I think it's a really interesting time to be in this work, because I think that there's going to be some really interesting solutions proposed over the course of the next few years about how to actually have a theory of management. And I bring it up because I think roles like the data product manager, or maybe someone who was an individual contributor as a data scientist at a company who kind of grows up into this role of saying, well, now I'm going to manage a team of data scientists and I'm going to manage this product or this portion of the product that really fundamentally relies on data science. How they do that, I think, will be really fascinating.
No, that is interesting. And having been a product manager myself, I'm kind of trying to, it was generally, we had market managers and product managers, and it was either market independent of product or it was product independent of market. In this case, how do you see the data fitting into this?
Well, interestingly, for many companies that have a core data science product, the users themselves are also the product, right? The users are generating the data. The users are creating that kind of fundamental building blocks of these products. And so having someone as that product manager who kind of deeply understands the fundamentals of the tools that are being used, but has experience on the side of saying, okay, well, what is the actual thing that what are we going to build that's going to make these our users, who also generate our product, use a product in a different way and enhance their experience and ultimately enhance the economics of our business, right? And so, like, the simple example that we think about a lot are, big social media companies that want to sell more advertising. How do you think about that in the context of a product manager, where there is this very, I think, subtle equilibrium that you have to think about between, creating value for your customer, your user, who then in turn creates value for your business, but not losing balance in that equilibrium where suddenly the customer becomes sort of self-aware of the fact that the things that they're doing on a platform are directly impacting their experience in a negative way. So seeing a bad ad or seeing too many ads or feeling like your data is not being protected, like things that have been very much in the public eye lately, having someone in place who kind of thinks about and takes responsibility for these things as not an individual contributor who's just thinking about building the next product feature is going to be really important.
Yeah, and I think what you're alluding to is risk management at the highest level.
Yep, exactly.
Risk management being around privacy being one area, but there's also a number of other sources of risk. And so maybe it's data independent of market and independent of product, perhaps something like that, unless it is the product, like you say.
Right. I mean, I think we're in a place now where we have to experiment a bit with these theories, right? We don't actually know, but I actually really like the idea of risk, because as someone who's building data science products, if risk is not a feature by which you make a decision, I think you're probably doing it wrong, because every single decision you would make that touches user data that ultimately feeds back into the product should almost certainly, right, almost, ipso facto would have risk associated with it. So how do you think about that, and how do you measure that, as you plan out product building and experimentation?
Yeah, and I think up until, let's say, this month, when I think it'll be in 2 weeks when the GDPR comes out of Europe, and it's going to effectively have an effect across the entire globe just by the nature and the way that it's written. People should have been thinking this way, but at least now, and we're focusing, in this particular case, it's focusing on consumer privacy, which again is a subset of risk, but at least that's going to force it from a legislative or a regulatory point of view that companies, at least larger companies that are going to sell into Europe, they're going to have no choice but to fold it into their DNA to a certain extent. So it makes sense. It makes sense at the highest level. And also, I think having this concept of a data product manager, a data manager, it makes a lot of sense, because an asset, one of the biggest assets of a company that's going to be a company that uses AI or data analytics as part of their core competency is going to be the data. And so that's a big asset. So you want to have a person or an organization really focused on it.
No, absolutely. Yeah. And I think one of the things that you bring up there that's interesting is this idea that, companies may be led to or making these decisions by external forces legislatively, and not even in the U.S. context. Clearly, like GDPR is a great example of this, may end up forcing companies to consider these things and start to build practices that might not otherwise have thought to do. And for me, I think that's a net positive.
Yeah, no, I agree. Well, let's switch gears a little bit, and I'd like to talk a little bit about AI, or a lot about AI, but I'd like to start off with just getting your thoughts on differentiating AI and advanced analytics, because a lot of times people conflate the two.
Yeah, so for me, I think one is being able to tell a good story from data, and the other is about automating decision-making from data. So, a lot of advanced analytics is about how do I understand, potentially at a very deep level, what all of this data can tell me, about my business, about my research, right? So if you have a bunch of data on your business and, let's say you run a consumer website and you just want to understand what are the top 5 reasons that we lose customers, churn analysis. What are the pathways to churn? And there are lots of really interesting analytical tools and methodologies that you could use to do that. And there's nothing unsophisticated about it, right? It is advanced. It's very, you can go really, really deep. But at the end of that analysis, the product that you're producing is effectively a story. Now, we might not think of it as a story. You might think of it as, here's a deeply technical analysis that I did of all of our churn data, and here are the top 5 pathways to customer loss, and here are some recommendations on how to improve that. But there's nothing about that that requires a piece of software to automate a decision or automate an observation away from a user. And I think as you move in the direction of trying to automate discovery or even further automate decision making and reasoning, that's when we start to move into a direction where I think we kind of traditionally think of artificial intelligence or AI as kind of being different. They may start from the same exact data sets. So taking the same example, if we said to that same company, we're going to do an analysis of how you're losing customers, and then ultimately what we're going to produce for you is a chatbot that attempts to engage with a user when we see them or we think they're moving on down a pathway to discontinuing service or unsubscribing. The building of that system, the building of that kind of automated bot that is looking for behavior on the website, doing pattern matching from that, and then automating an action and automating a response to a user. Now we're in the realm of AI. And for me, that's really the primary difference. One of telling a story and being able to learn from data, and the other trying to automate a action or a decision.
Well, let me run this by you because I don't know. I've been thinking about this as well, and maybe analytics is applying statistics, so a way of automating statistics. Maybe AI is applying analytics, maybe a way of automating analytics. Does that kind of fit your view?
Well, I would only say that, statistics is going to apply in all these contexts, right? Yep. So there, as a sort of formally trained social scientist, this is one of those sort of semantic differences that I think is worth digging in on a bit, only because there is sort of statistics for kind of what I would call summary statistics, where we think like, okay, what is the average time to something? What is our kind of median value for a customer? And to me, that's part of statistics. But then statistics also involves modeling and attempting to build a theory of how the world works, and how, in the context of, say, data science or in AI or interactions in a computer system, how humans are going to interact and react to different kinds of stimuli or information that's present in an interface. And statistics exists in both. I think the problem with people thinking about analytics is, in some sense, it's such an amorphous term. It can mean so many different things to different people. It's, in some sense, it would be more valuable to think of things that we could more cleanly separate, even though I think maybe these things have seams, not separations.
Yeah, no, I hear you, and you're right. I mean, you start dividing it down, and there's all the different types of statistics, and in particular, I think what's common throughout that thread, at least as applies to business, is going to be this, or the most effectiveness is going to be building models, right? And then we come down to cognitive models, which are built through, I more or less, divide it by machine learning, and then there's a whole variety of machine learning. So models that are learning versus models that are kind of constructed, which maybe you could classify more as advanced analytics. Does that make sense?
Yeah, I think that's fair. I think one of the interesting kind of distinctions without a difference that has come up recently is this idea that AI and deep learning are somehow kind of more advanced versions of machine learning, which is just fundamentally not true. I mean, right. I guess it's completely qualitative how one thinks that something is more or less advanced. Of course, folks who know the history of techniques like deep learning, I mean, they've been around for decades. And just as we were saying before when we were talking about data science, really the difference over the course of the last few years has just been the access to compute and the access to data. Right. A neural network in the 90s was an interesting toy for doing things like, number recognition in basic computer vision or OCR problems, and they were really good at it. We had small data sets of pictures of numbers that we could use to experiment, and that was sort of the ending and the beginning of that. And it wasn't until our more contemporary big data landscape where we have these tools to collect all this data and all this compute power to throw at it that we can see the results of these same techniques being extended to many, many more problems. And that's exciting. But machine learning as a general discipline is good at a bunch of stuff that deep learning is not really well suited for, not the least of which is unsupervised learning problems. I mean, the thing about the sort of basic traditional approach to doing deep learning is you just need a tremendous amount of training data to make the system work. You have to be able to define those, the networks within the deep learning model, and all of that has to be defined from data. And so you have that piece, and the other piece, which I think may come to a head over the course of the next several years, is just the interpretability problem, right? So much of what I think, AI as a discipline, what we now think of as kind of, or what is deep learning as a kind of sub-discipline of that, is so much of a black box by design that if we have to make really meaningful social decisions around it, right? If we're going to use these tools to do things like diagnostics in a healthcare setting and someone is misdiagnosed, well, the question is going to be why. And it's going to be really hard to answer that question if you just rely on a kind of black box AI model. Whereas with some more even traditional approaches to machine learning, just like linear modeling, right? If I look at the coefficient on a model, I know why a decision was made versus another one. So there's lots of distinctions in there that I think are important to make. The reality is, I think we're in a position now where we have enough competency, we have enough resources. It's exciting because now these tools and these methods are getting applied to places that I think, even a year ago people wouldn't have imagined.
Well, let's talk about that a little bit, and I'd like to get your perspective on what are the best use cases, or where are the tools best used for, and those tools being AI or and I guess in this case, I suppose we're going to say deep learning. I don't know, machine learning maybe.
Yeah.
And then analytics. Where would you apply each, or is there any generalizations that you can support to our listeners here?
Yeah. So I think, particularly in a business case, there's three questions that I like to talk to folks about, in terms of using data and using data science, and then maybe deciding on what the particular method or, what kind of machine learning model you're going to build. The first question I always ask is, do you think you even need data science to improve the product or improve the business? Or do you just need data? And what I mean by that is, we think about, all right, well, I have this business. I understand it well. I've heard about this data science thing or this machine learning thing. I know it's really exciting. People are making lots of money off of it. I want to do that. Yeah. And so sometimes what companies do is then they go and they try to hire a data scientist who tend to be kind of expensive. And they say, okay, now you're here. You're going to do some magic. Do it. But if you're a business who hasn't thought about, okay, how are we going to collect the data from our business? How are we going to store it? Why are we collecting this data versus a different kind of data? And ultimately, what specific question am I going to try to answer with it? I think you need to take a step back and say, you know what? Let's think first about what would make us a good candidate company for doing data science, or maybe what we really just need is a better way of accessing the data that we already have. And one of my favorite examples of this is, there's a company that I know here in New York that does commercial real estate analysis. And, I was working with them thinking about different data science approaches to doing some basic statistical analysis up to including more sophisticated modeling. And ultimately we got to a place where we sort of both mutually realized actually what they really needed was just cleaner ways of searching and displaying the very hard to access and opaque data that exists within the commercial real estate industry. And so they're a data company. They'll always be a data company, but it's unclear to me whether they ever need to be a data science company, right? They just need to be able to build well-designed
database company. Maybe.
Yeah, exactly. I mean, they need to pick those technologies and then build really well-designed products on top of it. Okay, so that's the first question. Think about, okay, do we even need to start with that? Okay. And then the next two questions are, okay, once we think that we have what we need, then what is where is the intersection between either the pain point, the most acute pain point you have as a business in terms of losing money, or potentially where you see the biggest opportunity for generating new revenue as a business, and how does that actually map to the data that you already have, right? The metaphor that I like to think of is like every business thinks about having, well, there's this low-hanging fruit thing that we think we could solve if we just had, maybe some data scientists to work with it. Well, if there is a low-hanging fruit, you want to pick the one that's sort of heaviest with data, because data science, machine learning, all that stuff is going to need a fair amount of data just to get started. So if you have a kind of low-hanging fruit problem or a set of low-hanging fruit problems, the best one to start with is one that you have the best and most robust data set for, and therefore it's kind of hanging lowest on the vine. So again, thinking about that intersection is always where I like to start when companies kind of talk to me about, all right, we want to make our digital transformation. We want to move into this new world. How can we start? And that's where you should start.
Okay. Yeah. And so far what I'm hearing, and I don't know your number 3 yet, but is data is the root of both of them. So one, do you have the data that you need, or do you have the data structured? And that could be structured meaning, are you laying it out? Are you labeling it to be able to do anything of worth with it? And then secondly, again, is if you are going to do something, you need that data. And right. So in both cases so far, the common denominator is having a data plan before having a data science plan.
Right. Well, and the third one is the pain point. Like, what is the business problem that is going to, either decrease costs for you? And I think oftentimes with data, there's a natural inclination to say there are observable things about our business that we should know, and probably the fact that we're not able to see them, or we're not looking at them because we're not looking at our data, means that we're losing money or leaving money on the table, right? Like from some of the folks that we've worked with at Alluvium, even if they're not good candidates for what we do, sometimes they're just in a position of saying, we're an industrial company, and the thing that we just don't know is who is our most reliable vendor for X piece of equipment. They might even have maybe decades of years of data on asset performance, and it's just sitting in a database somewhere, and no one's ever just looked to see, okay, what is the frequency of failure for this model versus another model, and when should we actually be engaging with a service provider for inspection versus when they actually do the inspection, and what is the more efficient way of doing that? Just actually observe, just being able to observe the things in your data that you potentially already have access to. Those are like the best first data science problems to go after.
Yeah, and I think what you're saying on the business problem, it's really going to be either decreasing costs, so it's going to be, operational efficiency, asset utilization, or the one you don't hear as much about, although in the marketing realm and the sales realm it definitely applies here, is increasing revenue, right? Is how do we increase innovation within our products? How do we invent new things? And these are all areas that we can apply data science, AI to. But the common denominator here in all 3 of them of your questions is having that data. And it almost reminds me of when you said it earlier, what a data scientist actually does, and you maybe have you can tighten up the statistics a little bit, but 80%. That's extracting, transforming, and loading, right? So data wrangling, 80% of the time. I don't know, 10% or 20% of the time, let's say 10 to 15% of the time is model building, maybe 5% of the time is inference. But maybe you can map that into the company's trajectory toward data science as well, in the sense that they're going to have to spend that 80% of the time on making sure they've got data before they can get to that 15 and that 5 to actually use it in an intelligent way. You know where I'm going with that?
No, absolutely. And I think your statistics are spot on. And I think for better or worse, quite frankly, that those numbers haven't changed a lot over the last, 5 or so years. It's, it would be interesting if somebody actually knew or could plot this, but my suspicion is that there's this very, very steeply increasing graph, which represents the amount of data that the average, sort of digitally native or transition business is generating year over year. And that's continuing to go up. But the quality of infrastructure and the competency of folks to be able to actually leverage that data is increasing at a much lower rate, right? Monotonically increasing at best, right? Yeah. And then the number of people, right, available to actually do that work is not increasing really that much at all. And
so if you plot it over time, for sure, it's going to be a long.
Exactly. So you have this long, unfortunate tail of companies that can really kind of grab all of the talented folks doing this for specific problems, and then there's just not a lot of people, or I would say, quite frankly, really well-designed infrastructure out there. I mean, some of that stuff is changing as companies transition and consolidate things around various cloud platforms. There's value in that consolidation just for sort of universality of tools, but having people who think about exactly the problems that you describe, there's still not that many people out there really good at that.
Yeah, no, and I think also maybe what's contributing to keeping us at this 80% is when we start moving into these more advanced machine learning techniques, the deep learning, for example, when you start using unstructured data and you start combining structured data with unstructured data, I'm just thinking that through, but that's got to make things way more complicated, doesn't it?
Absolutely. I mean, if you just think about the basics of a computer vision problem for classification, the classic one, like, is this a cat? Something like that.
I like the Chihuahua muffin one.
Yeah, that one. Yeah, that's a great one. Very challenging.
I love that one.
Yeah. So is this a Chihuahua or is this a muffin? So, it's unstructured data because it's just photos of both. But what does a deep learning model do except attempt to break up this unstructured problem, which is a photo, and generate a ton of structure around it, right? That's the whole process of training in a deep learning model, which is to say, okay, let me extract the grayscale of this image. Let me rotate the image 90 degrees. Let me digitize portions of the spectrum. Let me do all of these transformations in the data until I have a set of neurons aligned in the proper way that gives me the lowest amount of error on this particular training set. And the whole process of that is really one of algorithmically structuring a data set that starts as unstructured. And you could use the same exact case for unstructured text data, just a different process. I think what's interesting, especially now that a lot of deep learning tools have been commoditized through, lots of these really fantastic open source projects that are being pumped out by, Google and Facebook and OpenAI, what they're really doing is commoditizing that neural net, which is, all right, we've already pre-trained this computer vision model. If you're Google or Facebook, you have access to hundreds of millions or billions of images. No model may ever perform better than that. And so that structuring of an unstructured domain has been done already. And the question is, how will other businesses be able to find opportunities where that structuring hasn't happened yet?
Yeah, and I think the challenge there is going to be, what you're talking about is, I don't know if you could consider it, a certain number of layers, but then if you can take that learning that the Google has or the Facebook has because they've got a lot of a specific type of data that maybe your company doesn't have access to. But then the challenge is then to somehow put a fine point on that for what you're trying to do with your company. And so like transfer AI and there's a whole area now where is exactly what we're talking about, is trying to take learned models that are more looking at the basics and then transferring that, what's been learned in those models, and trying to fine tune them for your specific business problem. I'm not sure how far along that is, but that's the only way we're really going to be able to extract any value out of these existing models, isn't it?
I think that's exactly right. And I will say that is a big part of how we think about building value as a business at Alluvium. I think for many non-consumer companies, so enterprise companies in the space doing machine learning, AI, or even using tools like deep learning or others that we've mentioned, the huge disadvantage that they have, say, as compared to a Google or Facebook, is that their customers are not the product, and the data that they require to be able to provide value to their customers will never be theirs, right? When we talk to a customer, it is just, it's not a question. We're not retaining the operational data from a large industrial company because that data is their core IP. But as our system analyzes their data and begins to build its own internal structure that can represent how to, in our case, kind of understand the stability of those operations over time, that is something that we look to transfer both internally to that customer so that they show up the next day or they want to apply, they want to look at a similar data set from a different operation. Our value to them should be increased every time they use the system because that learning is transferable. But it also means that when a new customer comes around who has a similar, maybe not exactly the same use case, we tend to focus pretty specifically on, process manufacturing as a general kind of sub vertical of the overall industrial market. And so there is a fair amount of transferability, say, from one oil refinery to the next, but it's not exactly the same. But the advantage that we have is not that we can keep the data, but we can keep the models.
So this kind of, and I'm thinking this is gonna be relevant here, but it kind of brings up my next question, and I'll use the example of predictive maintenance. So process manufacturing, whether it's process manufacturing, discrete manufacturing, one of the biggest issues is trying to make sure that you know when the downtime is. So in this case of the process manufacturing, I guess I've got two questions. Can you transfer learning from, I don't know. I think I know the answer to this question, but can you transfer any learning from one client or from a model to a new client for predictive maintenance to make predictions on this, or is it just again too specific? And then it takes me to the question of because we can do predictive analytics, through traditional analytical, albeit advanced, but we can do it through traditional analytical techniques, or we can use deep learning, for example. But the deep learning, as you said, we just need tons and tons of data. So maybe you can unpack that for me, kind of help me out here, because it's a little bit confusing.
Yeah. So, we're very much squarely on this conversation is right on the pointy end of the spear, sort of just technologically. I think transfer learning as a practice has only recently emerged from academic work. There are a lot of challenges in building models that generalize to input spaces. That's just, mathematically, that is just a very difficult problem to think about solving. And so most of what we think about in traditional machine learning is we have a method that we want to use, and we have some training data that we can train on it, and then the test data or the data that we get from production is of exactly the same. It has exactly the same constituent pieces of exactly the same input vector. As we move into a kind of fuzzy transfer learning, a lot of this stuff is really new. So we think about it because we think there's value in being able to at least experiment and learn from moving essentially from a fully naive model to start, right? And the way that we do this is we want our users to be able to begin leveraging our product as soon as they have data to put in it. We don't want to limit them to only being able to use it after they've given us,
for years.
The first 100 failures of this asset or whatever the number is.
Which may take a long time, right?
Yeah, exactly. And so, we think there's a big advantage to having a relatively naive approach to start. Obviously, I mean naive in the sort of Bayesian sense of not having really strong priors about how any given input stream is going to affect the overall model and how we think about how these assets are performing, but actually leveraging the users themselves to provide ground truth back and move from a fully unsupervised approach at the start to one that is iteratively semi-supervised and increasingly supervised going forward. And the way that we do that is we kind of turn what our really industrial engineers and plant managers and SCADA analysts who use the software into data engineers, right? Actually providing labels back to us that allow the system to reduce the search space, to do automated feature engineering based on the interactions that we're getting back from users. And this is not like, we're not innovating that process, right? That's something that you would naturally expect for, say, a consumer grade product. When you show up to Amazon and you buy something, or you go to Netflix and you watch something, you sort of inherently know as a user, when you show up the next time, they're probably going to know a little bit more about your buying habits and a little bit more about your viewing habits, and your experience will be affected by that. But we want to use that same idea within the industrial context, mostly because, it serves us in many directions, but the two primary ones are, it means that our users get a better experience almost immediately, right? As soon as they use the system, it learns a little bit more and it's better the next time. And that trust building exercise is extremely important, particularly in the industrial space, where I think rightfully there's a kind of natural resistance to these sort of automated learning systems, I think based on years and years of failed attempts and betrayal by software providers, going back many years. But I think the other side of it is that it actually allows us to experiment more with this transfer learning piece, because we get to actually see and compare how users under not necessarily exactly the same context, but similar contexts are responding to how the system is working. And that allows us to actually test and experiment our own internal transfer models.
So for everyone listening, what I believe Drew is saying is that in this case, we're talking about using a learning algorithm, a deep learning algorithm to detect a failure that's going to happen in the future. And what you're saying is that, well, we can, there's certain base level calculations, let's call them that have to happen before we can get into the particulars of your particular pump in your particular oil refinery. So we're going to build on top of this learned model and then fine tune it to your particular problem. And the transfer problem, that we're talking about here, or the transfer idea is just that, is if can we transfer some lower level knowledge, I'll call it lower level, but some lower level knowledge in a way that we can build upon it so that we don't have to have all this data. And, quite frankly, this goes back to my question. First, I'm going to ask you if I'm interpreting what you're saying correctly. And then the second question I'm going to say is, why not use an analytical technique? Because we can find a failure signature, and we can do that through regression. Then we can match one signature to another signature with analytics, and we can say if they look the same, well, we can make a prediction. It may not be as accurate, but well, there's my two questions. One, was that a good synopsis? And two, why not just use just traditional analytic techniques? Right.
So on the first part, yes, I think that's a good summary. I think the way that I might describe it, outside of the machine learning context, is just think about it from the human learning context, right? So if you're an industrial engineer who works in an oil refinery, when you show up on the day one, nobody expects you to be an expert, but they expect you to be able to learn quickly. And let's just imagine then that, you're working at an ExxonMobil refinery for 5 years, and then you get a new job and now you're working at a Phillips 66 refinery. Well, those refineries are not going to be exactly the same, but there's going to be enough about the experience that you had in the first one to mean that when you show up on day one at the new job, you're not in the same position you were 5 years ago. Sure. And so when I think about transfer learning, that's essentially allowing for a computer system to have a similar approach moving from one context to the other. That even though all the input streams are not exactly the same, you should not be starting from square one.
It just is the same, right?
Yeah, exactly.
Okay.
Yeah. And on to your second question on the analytical approach, I think you're right. I think the challenge that we look to solve for is that predictive maintenance or asset failure is really just a proper subset of an overall problem that we really think about, which is operational performance. That if you can get really good at reducing the complexity of these very complex systems to make it much easier for a human to observe change and then interpret what that change means, then you will hopefully always be able to catch when assets are beginning to degrade such that they will fail. In some sense, that should be an easy problem for you to solve because the deviations from normal become apparent quite quickly. But the other thing that you should be good at, which I think moves beyond the analytical solution, is you should be able to see when things are having subtle changes that might not mean anything in the short term, but might be leading indicators of something that you haven't even thought of yet. It's this difference between thinking about, okay, I know that an asset has failed and I'm going to build a model on that particular kind of failure and then go look for that particular failure in the future. This is a kind of analytical solution to that. The problem is in practice, I think that what you would say sort of statistically is you're selecting on the dependent variable. Then in a sense, because you have a heavy selection bias in terms of your data set. Your data set is made up of a bunch of rare events because most industrial operations have failures fairly irregularly. Right. So turns out they're really good at identifying and preventing failure most of the time. And when failure does happen, it tends to be the result of something that was not necessarily extremely rare, but clearly got through a process that is a best practice and then still got over the line and failed. And now we have to learn from that. Well, that's exactly the wrong kind of data set to be building a model from, because you're only going to be building models on things that don't happen very much, which means you're going to miss all the other things that don't happen very much that weren't in your training set. And so anyway, a long-winded way of saying we think a general approach to learning from data as it's being produced and seeing good stuff and seeing bad stuff and having humans in the loop to guide the system is actually a much more straightforward approach to refining a model than only picking an analysis of, say, just failures.
So I think what I hear you saying is that you're going down this machine learning, deep learning approach because it's better. It gives a better result. And then secondly, the reason is, well, because you're looking at it's a more complex, I think you're looking at a more complex system then. If you start talking about overall operational performance, I don't know how many features are in these models. Maybe you can tell me that too, but this must be you're looking at a much bigger problem than, say, the friction, the coefficient of friction within the pump versus time, and just, a 2D simple. But I think you're saying that one is more accurate, and two, it's more accurate because we're taking in, well, first of all, we don't have this biased data, which I think is a great point, and two, we're taking in a lot more variables into this model than you traditionally do with a typical analytical approach.
That's right. Exactly right. I think the example you gave, I think is sort of right on a lot of the questions that we get from customers. If you talk to a customer in the oil and gas business, particularly if you talk to a petrochemical engineer who for many, many years has been using a really reliable set of physics-based models to understand thermodynamics and flow and pressure within a fluid catalytic cracker, and it's worked forever. And they say, why would I want to use a tool that doesn't take into account, at least not the kind of naive approach to doing it, doesn't take into account any of this institutional knowledge that I have. I know that that these variables are related to each other, and they typically have a scaling factor of X. And it's a really reasonable question. And I think there's no reason why these tools cannot exist together, right? The thing about machine learning is it's really good at identifying patterns and correlations and sort of systematic relationships that you would never think to look at because they're not part of these physics models, are not part of a canon of work that has come out of research. But there's no reason why you can't then overlay those two things together and enhance them both. And so we think about that as there's the naive approach to learning, which is we want a generalizable model that can take in some very high dimensional input space, an entire oil refinery, right? That might have hundreds of thousands of sensors on it. There's no possible way that a human.
How many features are in the model? Hundreds of thousands?
Well, you can certainly have hundreds of thousands of input streams, right? If it's every sensor on the plant, you can have that. And what the system is good at doing then is, in an automated way, generating a set of features that accounts for many or all of those input streams. Literally, what we try to do is build models that can predict the output of any given input stream at any given time based on whatever history we've seen of it. And that is that big multi-level, many-layer network for doing that produces those results. And then what the products actually do is simply compose all of those outputs together so that instead of having to track maybe maybe not 100,000, maybe it's 5,000, or maybe it's a couple hundred, but even at that scale, it's very hard for even an expert to do kind of this high dimensional calculus problem in their head at any given moment. But a computer is really good at that. And the generalizable way that I think about it is that in any given setting where there's lots and lots of input data, and the question that's posed to the humans are, interpret this data, use it to make better informed decisions, right? If you have transparency into a system through data, the theory is you should be able to make better, more well-informed decisions about what to do with those resources based on that information. But there's this natural tension then, which is, okay, as a person who's in that situation, I can either put a bunch of resources into discovering novelty in that data, looking at it, analyzing it. I mean, in some cases, physically standing in front of a monitor and looking at a graph on a screen to see how it changes. That's very resource intensive, and quite frankly, human cognition is not really well designed to do that. But a computer is really good at that. And if you particularly with modern techniques, when we're talking about deep learning, like really good at taking a bunch of input streams and doing that automated structuring of that data to build, say, a many layer network that can interpret these things and make predictions. But the other side of that tension is, all right, once I've discovered something novel in the data, how do I reason about what it means? What does that change actually mean? And as you can probably see where I'm going with this, but that is a thing that computers are really bad at doing, right? They're not
specifically black box algorithms.
Exactly, who have only really been trained to parse out where these patterns exist and how they relate to each other. But a human is really good at that. And in particular, a human has maybe decades of experience working in a particular area and has a deep amount of expertise. So if you can build a system that kind of rebalances that tension, where it moves the person to having to spend much more of their time just reasoning about what change means, and then allowing the computer system to learn from those observations how a person interprets what that change means, so that the next time those alerts or that information gets presented to that person is even better, or even of a higher value, then I think you've built a good system, right? You've built something that has a kind of positive feedback loop where there's value being built on both sides, both for the computer system that gets better, and for the user, for the person who has better, more accurate information being surfaced to them.
Yeah, and I think maybe one answer to your clients that say, we've got these, thermodynamic models or whatever physics models we've been using for years. The reality is that they're still theoretical. And when you put them within a real world environment, that's where AI shines, because it's going to take, what's the pressure? What's the air pressure? What's the temperature? All these other factors, what shift was working, all these other factors that affect a theoretical model. That a theoretical model just can't grok. It just can't calculate. So, there's the area of using a model of a model, so models of models, and using the theoretical to somehow guide the AI models. I don't know if that's what you're kind of alluding to, but that's an area of work in analytics is happening where you've got the model of models that helps define the statistical model, at least guides it. Like, for example, gravity. You don't have to reinvent gravity or statistically sample gravity. If you can have a model of model knowing that gravity is part of this system, then it helps from an analytical point of view get to a solution quicker. And I'm guessing if there's a way of merging the two, that's the best of both worlds that you've been talking about.
Yep, I think the example that comes up a lot for us is it's sort of two different versions of the same question, which is one, can your system help us better understand which, we would call them features, they would call them, tags or sensors, should we really be paying attention to, throughout the course of the day? What are the most important pieces of information that we should be looking at? Because they probably, just as you said, they have their kind of their bias from the training that they have. This is okay, well, this kind of pressure is what's most important when you start a particular kind of run, or make sure you follow the thermodynamics for the first hour of this, because that's when things are typically the most volatile. And those are all great rules of thumb, and obviously that's part of a work process. The other version of this that we hear has more to do on the investment side, which is, okay, we know we're going to invest a couple $1 million in new sensors. What kind of sensors should we do? Which are the ones that provide the most value? Should we be adding new thermal sensors? Should we be adding power consumption, vibration? What should we do? And for us, those are features that can fall out of the model, and so that's something that we can provide value to the customer, and sort of having that conversation around optimizing for input streams.
Yeah, and that takes us to the data and having the right data. But let me ask you this question, because I almost threw in the predictive maintenance as a red herring here, but I can see where you're going with it and why AI is good for it. But generally, or AI in this particular case, what we're talking about is deep learning. But generally, the way I think about deep learning and what it's good at is like the human senses. It's whether it's handwriting, whether it's visual, whether it's audio, whatever the other senses are. But here now we're talking about something that's none of that. So beyond what you can see, what you can hear, what you can feel, and so forth. What are the other use cases? And that goes back, I guess, to an earlier question I had. But what are the other use cases where deep learning, and I guess we're going to use that synonymously with artificial intelligence for these purposes? What are the other areas that it's good at besides recognizing this chihuahua, hearing this heart murmur, seeing, recognizing the intent of the sentence? What else is it good at? Predict. I mean, this is one of them, but how do you classify that more generally?
Right. So I do think it gets back to the earlier discussion around kind of where are the most high value problems to be solved from unstructured data? Because the thing that deep learning is really good at doing is, if you have a lot of unstructured data, certain approaches to it will allow for you to, again, kind of automatically structure that and begin looking for things. Now, of course, the other side of that is you can have lots of unstructured data, but there's one really important piece of structure that it has to have, which is typically a label, right? So in the Chihuahua case, is like, this is a picture of a Chihuahua, this is a picture of a muffin. Right. Even though to the human eye they look very similar, we can tell a computer that very sort of discrete difference, and it will start to learn the difference and perform well. So in the industrial case, there's lots of examples of where you have, sort of computer vision problems that are well defined and can generate good labeled data. And so actually I was at a conference a few weeks ago, and it was a machine learning and oil and gas conference. And there was a fascinating example of how there was a computer vision algorithm that was applied. It was using, deep learning. It was actually using really contemporary approaches to doing this to be able to identify toxic spills in a refinery environment, or even in an E&P environment, as well as being actually able to identify not just if a gas leak had happened, but what the specific kind of gas leak it was, which of course required video data from the non-visual spectrum, either infrared or otherwise, to actually be able to determine what was in that leak. Mm-hmm. And the interesting thing, of course, to me, is that the technology that they were using to build the deep learning model was, maybe 10 to 15 lines of code, leveraging lots of open source technology to do it. The much harder challenge was building a training data set that said, oh, this is a video of a methane leak, this is a video of a carbon dioxide leak. To the naked eye, they look indistinguishable from one another, but we're training the system, and they actually were not forthcoming with the process they used to generate the training data, because my guess is that's really what the secret sauce is, right? And so there's lots of places where you could see deep learning being really valuable. Like another one that is not just true in the industrial space, although it comes up a lot, is using text data to analyze work orders and invoices. Looking for errors, using for automated approaches to auditing, because a lot of times there's some structure in the data, like the PDF has a specific form to it, but there's lots of other information, particularly the text itself, which may be ripe with encodings and jargon and all kinds of things that someone has to go in and label as, oh, this is not right, or this is an auditing mistake, and then use that to build a model. So honestly, it comes back to the 80-20 rule that you described. I think there's lots of opportunity. The question is, are companies going to invest in actually generating good training data so that they can then apply these techniques?
Yeah. And it seems like, what I'm trying to answer for people listening right now is, where do I apply this? And it seems like predictive maintenance is almost an outlier here, because all your examples were either image, video, or text, or audio kind of examples, right? I mean, and then we have got this predictive maintenance one, which is a little different. Well, so far everything has been in that realm of the senses. Is that pretty much the rule of thumb? Well,
and the other one that we deal with is on time series data. And there's a lot of really good approaches to analyzing time series data with either sort of traditional time series approaches in machine learning or deep learning, and in particular, using techniques like long short-term memory, or LSTM, which is something that we use to be able to take these very high-dimensional input spaces of time series data and apply structure to them that actually learns how these things are related and correlated to each other. That is something that we narrowly focus on as a business, but I don't want to leave it out. I think the lack of structure that we're imposing through the modeling there has to do with how these input streams are related to one another. Not that time series data is unstructured, but it is sort of lightly structured in many cases, because the unit of analysis there is just a value with a timestamp. And then typically you may have a specific label like, oh, it's sensor X, but you might not know anything about the physical way that a system is laid out. And in fact, you might not want to, because it's maybe more valuable to just take these things as a whole system and then impose structure on that based on what the data is telling you.
No, I like that. And I think that's a good way to kind of close things off, because that takes us to the Internet of Things.
Right.
And if you think about, the data, at least the internal data that's coming from the Internet of Things, it is time series-based data coming from sensors. And that's kind of where I was hoping you were going to go with this, because, you're going to have, if you think about it in a big spreadsheet, you're going to have whatever number of columns these variables are, however many sensors you are, and then how many dimensions are per sensor. But then the rows, right? It's going to be the time, and you can have literally hundreds of thousands, if not millions, of data. And I think that is a nice and interesting area to kind of bring the two worlds together. We finally said the word IoT. We set it up to this point, but right, that seems like that data is made for finding out, and again, looking at it from a system perspective, because I think that is a very important point for people to get out of the conversation from what Drew's been saying, is because it's a whole system, and you can't look at it in isolation, and you can't theoretically model it because it's just too complicated. So looking at this whole sensor map as a whole system, there's probably a lot of value, and that's maybe for another discussion, but there's probably a lot of ways that we can train the models in different ways to, I guess, at a high level, extract value.
Yeah, and if folks are thinking about this in a sort of general way, the best approach to using deep learning or machine learning in this context is dimensionality reduction, or simplification of system, right? And the way that I've thought about it in lots of contexts is getting back to that decision maker, the person standing on the platform, the person in the warehouse, person at the facility who has to make a decision from data and is typically under some constraint. That constraint can be time, it can be resources, it can be a combination of those things. And so if you build a piece of software and a learning model that allows for them to more efficiently observe change and ultimately make a decision from that data through, dimensionality reduction being a technical term, but really just through simplification of system, that's a huge opportunity in the sort of general Internet of Things, because everything about the Internet of Things, particularly as they scale up, and not just on the consumer side, but on the enterprise side as well, is all about high dimensional problems, whether it's, thousands of sensors in a facility or thousands of people wearing a wearable. All of these things are very high dimension.
Right. So use that meta model to a certain extent to help us with this dimension reduction, and that could be a nice combination there.
Exactly.
All right. Well, that's excellent. Well, Drew, tell us how our listeners can find out more about you and your company and what you do and so forth.
Yeah. So for me, I'm an easy Google, but my Twitter handle is just at Drew Conway. That's DREWCONWAY. I'm pretty active there and love to chat with folks. My website's just drewconway.com, and you can reach out to me there. Alluvium, same thing. Our website is just Alluvium, ALLUVIUM.io. Twitter handle's the same, just Alluvium. And for folks who are interested in learning more about the company, you can contact us directly through the website, and there's demo videos and things that you can watch to see the products there. We'd love to hear from you. Folks who are thinking about these problems, either in the short term or long term. It's always great to hear from folks who are dealing with this stuff every day.
And, just to be clear, I mean, you've kind of hinted at it in a few different ways, but you're dealing in an industrial setting. Mostly you said process
right.
manufacturing, but there's other areas, and you're applying AI to it. Can you give a little bit more color to it to understand what you do?
Yeah. So our flagship product is called Alluvium Primer, and Alluvium Primer is really designed to support folks in an operational role who are managing resources. So the way that we use AI in this case is essentially to generate a dashboard and then ultimately a report that is a prioritized list of things that a plant manager will likely want to know about and need to make decisions on, say on a daily or twice at shift change basis. The challenge that we saw in the market from a say a simplification problem was that plant manager shows up at a facility, say 6-7 o'clock in the morning, and if it is a process manufacturing facility with continuous automation, that means the first question on his or her mind is, what happened overnight? What happened in the plant overnight? What do I know about? And the way that question gets answered today is through, quite frankly, a very manual process. I mean, we've had folks, our customers tell us, when we ask the question, well, how do you do this now? It's, we talk to each other in the hallway. I walk around and look at my favorite, gauges, or I do a quick spreadsheet analysis. And obviously things get done and they get done quite well, but there's clearly room for improvement there. And quite frankly, room for reducing, mistakes or reducing false negatives. So that's exactly what Primer is designed to do. It doesn't change how they make decisions. It doesn't change how they run their plant. All it does is it hopefully makes them much more informed at the point at which they need to make those decisions.
So it's using AI, all the above, to, present the information or the data in a way that it can be acted upon.
Exactly. Yeah. Our goal is we want our plant managers to have access to the most pertinent information at the most appropriate time and allow them to make those decisions as efficiently and as accurately as possible. And the AI is really the means by which that information gets to them.
Drew, excellent. Thanks a lot. We'll be talking soon.
Bruce, my pleasure. Thanks for having me.
Okay. That was a good talk with Drew Conway of Alluvium. This podcast goes vertical, deep diving into different topics each week. If you prefer a more horizontal and structured approach to learning IoT business and its orbiting technologies, check out my book IoT Inc., published by McGraw-Hill, or become a certified IoT professional by completing the ICIP training and certification program. For details, just go to www.iot-inc.com. Also go to www.iot-inc.com for an analysis of this episode, links to things that were mentioned during the episode, and very importantly, the episode's PDF transcript. Just search for the name of the episode or the guest. If you're new to this podcast, subscribe. That way you'll get every week's episode delivered straight to your device. Or, if you've been listening for a while, there are 3 ways you can support the show. You can leave a rating or a review on iTunes. Just go to iot-inc.com/iTunes. It only takes 1 click to leave a rating, a little bit longer to leave a review. You can share it on social. I'm on LinkedIn, to a lesser extent on Twitter. And of course, you can support the show by buying my book, IoT Inc., or the ICIP training and certification program. It's how I pay the bills. Next week's episode is Convolutional Neural Networks for IoT Time Series Data with Simon Crosby. I hope you can join me then. I'm your host, Bruce Sinclair. Thank you for listening. Till next week, may your path to IoT business be a deep one.
You have been listening to the IoT Inc. Business Show.